Let's look at Mass-Spring-Dashpot Systems. A spring is stretched 10 centimeters by a force of 4.8 newtons. That's about 1.08 pounds. A body with mass 3 kilograms is attached to the spring. Find a general equation for the resulting motion. If we have an object with mass m attached to a spring with spring constant k and the damping constant for the system is b, then the position y of t of the object satisfies the differential equation my double prime plus by prime plus ky equals 0. This is called free motion. There is no outside force acting on the object, nothing pulling it back and forth, nothing like that. By the way, an object that resists motion is called a dashpot. Here we're not told of anything that's resisting motion. Sometimes, in some problems, friction plays the role of a dashpot. But not in this particular problem. No dashpot here. M equals 3. We're told that's 3 kilograms. That's the mass of the object. K, the spring constant, we need to calculate that. F equals ky by Hooke's law. F is the force attached to the spring. K is the spring constant. So in this case, the force is 4.8 newtons. Got to measure it in newtons. K, well, that's just K. And y is the distance that the spring is pulled by this, by this force. Well, the force is 4.8 newtons. Everything has to be measured in meters. We were told earlier that it was, the distance was 10 centimeters. Well, you got to convert that to meters. So it's going to be 0.1 meters. 10 centimeters is 0.1 meter. So K equals 4.8 divided by 0.1. In other words, 48 newtons per meter. This differential equation, plugging in m equals 3 and k equals 48, becomes this, because b equals 0. There's no damping, nothing slowing it down, so it's what we call undamped motion. So we get this differential equation. Awesome. Okay, let's solve it. I'm going to divide everything by 3. We get y double prime plus 16y equals 0. Therefore, you remember how to solve a differential equation like this. This is going to be r squared plus 16 equals 0. So the solution, because r squared equals negative 16, r is going to be plus or minus 4i. In other words, 0 plus or minus 4i. That leads to a solution of the form y equals k1 cosine 4t plus k2 sine 4t. Here's another way to solve the problem. Undamped free motion, that is when b equals 0, y of t satisfies the differential equation my double prime plus ky equals 0. The solution will always be y equals a cosine omega t plus b sine omega t, where omega, I know it looks like a w, but it's the Greek letter omega, where omega equals the square root of k over m. For example, in our case, omega is the square root of 48 over 3, which is square root of 16, which is 4. Thus, the solution is y equals a cosine 4t plus b sine 4t. That's the same as what we had a moment ago. We were just using a and b instead of k1 and k2, but same difference. Okay, find the equation of motion y of t if the spring is set in motion with initial position y0 equals 0.3 meters. Well, it should be 0.3 meters. Sorry about that. And initial velocity v0 equals negative 1.6 meters per second. So this is an initial value problem. This was our general solution. Therefore, when t equals 0, well, we know y of 0 equals 0.3. We were told that. And y prime of 0 equals negative 1.6. We were told in a moment ago y prime is the velocity. Let's plug in 0 into this equation. Okay, y of 0 is just going to be k1 because sine of 0 is 0. So we just get k1, and that's going to be 0.3. Y prime of t, okay, let's calculate the derivative. Y prime of t is going to be negative 4k1 sine 4t plus 4k2 cosine 4t. Plug in 0, and again, sine of 0 is 0, so that's going to drop out. We're left with 4k2 cosine 0 equals negative 1.6. That comes from here. 4k2 cosine 0 equals negative 1.6. 4k2 equals negative 1.6 because cosine of 0 is 1. Therefore, k2 equals negative 0.4. So y of t equals 0.3 cosine 4t minus 0.4 sine 4t. That's the solution to this initial value problem. Find the period, frequency, and amplitude of the resulting motion. Okay, undamped free motion y of t satisfies this differential equation. Solution is going to be y equals a cosine omega t plus b sine omega t. We saw that a moment ago. The period is 2 pi over omega. In other words, the period is how long it takes to complete one full cycle. 2 pi over omega, which in this case is 2 pi over 4, or pi over 2, so it's pi over 2 seconds per cycle, which means the frequency will be the reciprocal of that, namely omega over 2 pi, which is 4 over 2 pi, or 2 over pi cycles per unit time. So that's 2 over pi cycle, so 2 over pi cycle per second. Let's graph y of t equals 0.3 cosine 4t minus 0.4 sine 4t and see if we can figure out what the amplitude is. That's the one last thing we need to calculate here. Wow, that amplitude looks like 0.5. Looks like the amplitude is 0.5. Actually, it is 0.5. The amplitude of y equals a cosine omega t plus b sine omega t is the square root of a squared plus b squared. So y is going to be 0.3 cosine 4t minus 0.4 sine 4t. The square root of a squared plus b squared is the square root of 0.3 squared plus negative 0.4 squared. Turns out to be this, which is the square root of 0.25, which is 0.5. Okay, so the amplitude is indeed 0.5. Different problem. A body with mass of 3 kilograms is attached to a spring with spring constant k equals 1/4. The damping effect of friction, that's why this is a Mass-Spring-Dashpot problem. We've got some friction, we've got some damping. Damping effect of friction is equivalent to a damping constant of b equals 2. Find a general equation for the resulting motion. Okay, we were given this differential equation earlier. We're told that the mass is 3 kilograms. B, that damping constant is 2, and K, the spring constant, is 1/4. So this is our differential equation. I don't want to deal with fractions. We're just going to multiply everything by 4 and get 12y double prime plus 8y plus 8y prime plus y equals 0. Okay, we know how to solve something like this. Okay, we've seen earlier that you just convert this to the equation 12r squared plus 8r plus 1 equals 0. And how do we solve that? That's a problem for the quadratic formula. And you remember that from 7th grade or 8th grade or whenever you had it. The opposite of b plus or minus the square root of b squared minus 4ac all over 2a. Plug in everything. We end up with this because a equals 12, so that's going to go here. B equals 8, so that's going to go in various spots. And c equals 1, so that's going to go here. Okay. That simplifies to negative 8 plus or minus square root of 64 minus 48 over 24. Negative 8 plus or minus the square root of 16 over 24. Negative 8 plus or minus 4 over 24. That's, in other words, negative 4 over 24 and negative 12 over 24, which simplifies to negative 1/6 and negative 1/2. Those are our solutions for r. So the general solution to our differential equation is y equals c1 e to the negative t over 6 plus c2 e to the negative t over 2. Suppose that y of 0 equals negative 4, y prime of 0 equals negative 12. Solve the initial value problem, resulting initial value problem. Okay, this is the general solution, but now that we have a couple of initial values, we can plug those in and find out what c1 and c2 are. So we plug in t equals 0, and this is what we end up with, but e to the 0 is just 1. So y of 0, which is negative 4, and this is going to simplify to c1 plus c2. So we get negative 4 equals c1 plus c2. Great, we've got one equation. When we take the derivative of this, we get y prime of t equals a negative c1 over 6, e to the negative t over 6, minus c2 over 2, e to the negative t over 2. Plug in 0, and this is, of course, y prime of 0. This stuff, well, we know what that simplifies to. E to the 0 is just going to be, that's just going to be 1. So y prime of 0 is 12, and all of the stuff on the right side simplifies to negative c1 over 6 minus c2 over 2. Okay, we've got a system of equations. The solution to that system of equations turns out to be c1 equals 12, c2 equals negative 16. So the solution to this differential equation is 12 e to the negative t over 6 minus 16 e to the negative t over 2. Awesome. Graph this motion. That's what Desmos is for. That's what we end up with. Determine how far the object moves to the right, moves in a positive direction, before it starts moving back towards the origin, towards equilibrium. Well, based on the graph we saw a moment ago, gosh, it looks like it makes it as far as 4. Y-coordinate at this point appears to be 4. Coincidentally, that's the x-coordinate. Well, kind of. So I'd say 4 meters because that is the y-coordinate at this point. You might think that's kind of cheesy. Let's graph it and make sure. When I graph it, it turns out that the maximum is indeed y equals 4, and it doesn't actually occur at x equals 4, time t equals 4. It's actually a little bit beyond that. So yeah, we can see that the maximum value from our ti, yeah, that's y equals 4. So that is indeed how far it moves in a positive direction before it starts moving towards equilibrium, 4 meters. Determine when the object first crosses the equilibrium point. This should be an E. The letter that comes after D is E. Okay, so this again is our function, and we want to figure out when it first crosses the equilibrium point. That's a matter of just graphing the function on your TI, and it turns out that the 0 for this function is x equals 0.86304, blah, 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 blah. In other words, t equals 0.863 seconds.